Here we're going to provide an example of how do we figure out if a state is transient or recurrent. Now, this isn't, what I'm going to show isn't intended to be a proof, but our goal is to give you some guidance or kind of understanding of what these things look like in practice. Okay, so this was the initial Markov chain that we had started off with. We had states 1 and 2. We have 1/4, 3/4, and then 1/2 and 1/2. All right. And the question is, are states 1 and 2 transient or recurrent? We already know that they're not absorbing. Okay. So what we want to check for is we want to say, hey, if we take the sum of n equals 0 to infinity of p to the n power, and we're going to pull out the I term. And so here I is either 1, 1 or 2, 2. We want to check, is that less than infinity or is it equal to infinity? So why don't we put equal to? All right. So the way that we can go about checking this is we can say, well, let's start by defining our P matrix in MATLAB. And so I'll go ahead and fill it in. So we'll have 1/4, 3/4, and then 1/2 and 1/2. So now we have our P matrix. All right. So let's say we were focusing in on state 1. Okay. So the sum of n equals 0 to infinity of p to the n 1, 1. So we'd start by taking out oh, and I made a mistake. This should be 1. I'm surprised I did that. We start by taking out the 1, 1 term. So we get 0.25. Okay. So we have 0.25 there. Okay. Plus, we're now going to take out the 1, 1 term for p squared. Okay. So when we do p squared, we get 0.4375. All right. We're now going to take p to the third power. And we get 0.39062. All right, let's take it to the fourth. And I'll do this a bunch of times. 0.402. 0.399. 0.400. There's actually a 1.5, but I'm just going to round. Right. Take it to the seventh. Again, we get pretty much 0.0 or 0.400. And in fact, if we keep doing this, we start to see that this 1, 1 term, this first entry, sort of converges to 0.4. So what we're going to end up with, if we want to think about it, is we're taking this summation to infinity, so we're going to have infinity of these 0.4s. So if we add 0.4 plus 0.4 plus 0.4, 0.4 plus 0.4, 0.4, right, this summation is not going to converge, and so it's going to go to infinity. So in fact, this tells us that state 1 is recurrent. All right. Alrighty. Okay, now let's check state 2. Now we've already done a bunch of the work on the right-hand side. So we're going to do the same thing. We're going to take the sum of n equals 1 to infinity, p to the n. But now we're going to pull out the 2, 2 term. And so we've done some of this work. So I'm going to scroll up on MATLAB. And in this case, we're looking at the 2, 2 term, which is in the bottom right. So we're going to get 0.5, plus 0.625 plus 0.593 plus 0.602 plus, let's see, let's scroll down, point what? 0.600 plus 0.600, and all of a sudden what we see is that we keep getting 0.6. Okay, so here you have p to the 10th, p to the 11th, we see 0.6, and it just keeps adding up 0.6. And so if we keep doing that, so we're going to keep adding 0.6 plus 0.6 plus 0.6 plus 0.6. We're going to do that basically infinity times because our summation goes up to infinity. We keep taking p to the n power and pulling out that 2 term. So because we're adding a constant over and over and over again, it's going to add up to infinity. All right. So in that case, this will end up being infinity, which will imply state 2 is recurrent. All right. Now, let's do an example where we don't have recurrence, and you'll sort of see the difference of what's going on. Okay, so I'm going to do a very simple example, and hopefully we can sort of figure it out. I'm going to have state 1 and state 2. We're going to make state 2 an absorbing state, and we're going to say 1/2. Oops. With 1/2 probability, you go to 1 to 2, and with 1/2, you stay. What's going to end up happening? So we already know, in this case, that state 2 is absorbing. What we're going to show is that state 1 is transient. All right, so let's sort of see. We'll sort of do it numerically and we'll kind of show it. Okay, so our P matrix here is going to be 1/2, 1/2, 0, and 1. Right. So, again, for state 1, we're going to add the sum of n equals 1 to infinity, p to the n, and we're going to pull out the 1 term. All right, so I'm going to go over to Octave and we'll start calculating that. So p is equal to 1/2, 1/2, 0, 1. All right. So we're going to p to the 1 power. We're going to pull out that 1 term right here. So we get 0.5. All right. Let's take p up 2. Now we're going to pull out 0.25. Let's take p to the 3rd power. 0.125. P to the 4th power. 0.6025. And you should be noticing a pattern that the number that I'm adding keeps getting smaller and smaller. And in fact, it's basically dividing by 2. So for an arbitrary n, I think what we have is 1/2 to the n power. And we keep adding these continuously. So I can in fact rewrite this. This is in fact the summation of n equals 1 to infinity over 1/2 to the n squared. Now, if you remember your calculus, or this might look familiar from calculus, this is sort of like an infinite series problem. And what we want to show is this actually converges to a value. Okay, I think this is called the geometric series, but let's go ahead and check that out. go to Wikipedia. Yeah, in fact, we see the geometric series right here. Okay, so let's go to Wikipedia and figure out what the summation of this geometric series is. Now, this probability is just for this particular case. So I don't want to, it's not going to generalize to all problems. Okay. So here's what we have, a to the r to the n power. Okay, so here goes, if you can see that, can't really highlight it, but here goes the formula. All right. And so we're going to go ahead and use that. Oh, no, that's not the formula. Why did it scroll down? Here we go. Yeah. This is the formula we want to do. So we're doing some summation of r to the k power. Now our r is 1/2. Our a is equal to 1. Right. So I'll go ahead and rewrite this. So for a geometric series, I think that's what the summation is equal to. Yeah. Okay. So in our case, that's what we have. All right, so a is just equal to 1. R is equal to 1/2. So this summation actually converges to 1 over 1 minus 1/2, which I think is equal to 2. Now, this summation is less than infinity, which implies that state 1 is transient. Cool. All right, so here goes an example of how we can sort of, I don't want to say prove, well, in this latter case, we actually proved transience of state 1. All right, it's not always going to be so straightforward if we have a really complex Markov chain. But hopefully this gives you some idea of how we can sort of check for it. So in the first case, what we did is we kept taking this p to the n power, and we saw that these numbers converged to a single value. So these values converged. And when you add up the same value an infinite number of times, you always get infinity. Now in the transient case, when we took p to the n power, what we saw is that that series went to 0. Not only did each individual value converge to 0, but when we summed them up as part of a series, they converged to a finite value, okay, less than infinity. And so that told us that the state that we are interested in was transient. And so that's a pretty good test of how we can check for transience.